In this lesson, we'll talk about implicit differentiation. This is a bit of a strange topic, but it's actually very useful for solving new problems. Here's the idea. If you want to take the derivative of some very strange functions, functions that might not be really defined necessarily by y equals something, we need a new technique. Let's start off by what we call an implicitly defined curve. An implicitly defined curve is exactly what I was just mentioning. It might not be written as y equals f of x. That's what we call an explicitly defined curve. For example, we've got x squared plus y squared equals 25. That is a curve that you are very familiar with, namely the circle of radius 5. But that is a implicitly defined curve. Think about it. If I were to try to draw a circle, wouldn't it fail the vertical line test? That's because a circle is not a function, but this equation does tell us something about the circle. The implicit differentiation idea is how to take a derivative of a function of this style. It might be nice to get a feel for what sort of tangent lines are going on that circle. The next example is this kind of strange one. X cubed plus y cubed equals 6xy, which is known as the folium of Descartes, and we have it drawn here. As you can see, it's got a few different things going on with the tangent lines, but at 0, 0, that's a little unusual. There's some strange things that happen there which we won't talk about in this course. What can be done is often with these sorts of functions, they have to be separated because they're not functions. As you can see, this definitely fails the vertical line test. You could, however, kind of splice it maybe here to take this piece. We could also take this piece and maybe cut it for this piece. It would look strange, but the computer could do that. And then maybe you could take the derivatives on those specific pieces, but isn't there an easier way? This is the easier way. Implicit differentiation, we sort of assume that y is a function of x. It's not a function of x, but the rules still apply. That if y is something that's related to x, then it still holds that we can find y prime based on the y that associates with each of the x's. This is the idea. First, you take the derivative of both sides, and the key is do it with respect to x. Now I'll show you guys plenty of examples with this. We do assume that y is a function of x. And the reason this works is because y generally can at least be split into multiple functions. What happens is every time we take the derivative of something that has a y in it, we use the chain rule and get a y prime. Y prime is what we're looking for, and so we just solve for y prime. Let me give you the first example. We've got x squared plus y squared equals 25. We take the derivative with respect to x. With respect to x, x squared becomes 2x. Now think of y like we did in the previous section with the chain rule. Think of it as y is like my u. My outside is the 2. So u squared would become 2u, but it's y this time. And then I would multiply by the derivative of the inside. Think of y as an inside function. You use the chain rule in that you say 2y, but then you multiply by the derivative of the inside and get the y prime. The derivative of 25 now, because we're taking the derivative of the whole thing, is 0. That probably looked a little bit complicated, but we have more examples. What we're going to do now is just solve for y prime. If I subtract 2x from both sides, I get 2y y prime equals negative 2x, and I'll divide by 2y and simplify to get that y prime is negative x over y. The derivative in this case is dependent on both x and y. That's not as strange as it sounds though. It's okay because we can still plug in a value of x and y to find the derivative slope here. The slope is found by taking y prime at the point negative 3 and 4. I get the negative of negative 3 over y. There's my negative x over y. And I get 3/4. I've got a point, I've got a slope, so let's do the point slope form. Y minus 4 equals the slope times x minus negative 3. We get y minus 4 equals 3/4 x It's going to be a plus 9 over 4. So we get y equals 3/4 x plus 25 over 4 is what I get. You can still find the equation of a tangent line even when it's not a function. If it's implicitly defined, that's good enough. We use implicit differentiation, and we find the slope of the tangent line and thus find the equation of the tangent line. Here's your phoneme of Descartes. Let's find the derivative and then find the equation of the tangent line at 3, 3. Same process. Take the derivative with respect to x. The derivative of x cubed is 3x squared. Y cubed is again that composite idea, but either way I get 3y squared y prime. The question you might be asking yourself is, does that work every time? Yes. You may take the derivative with the y, with all the rules that you're used to for x. The only difference is that after you write it down, you multiply by y prime. This is the chain rule. However, right here is a little bit different. Let's think of this as a product. That's the thing. Y is a function of x. So anytime you see x or some expression with x multiplied by y, we have to use the product rule. The product rule says the derivative of the first times the second plus the derivative of the second times the first. Let's just clean this up a bit. 3x squared plus 3y squared y prime is still here. The derivative of 6x is 6, so I get 6y. And just rearranging this multiplication, I get 6x y prime. You needed the product rule whenever you had y times a function of x, because again, we're thinking of y as another function of x. If you have x times another function, you have to use the product rule. Now we're at a point where we can use our rule. One of the things that I see that I'm going to do to simplify this is I'm going to divide everything by 3. What we do now is we get the y primes on one side, and that's how we're going to solve for y prime. I'm going to subtract x squared from both sides to get it over here out of the way. And I'm going to subtract 2xy prime from both sides to get the y primes by themselves on one side of the equation. So I get y squared y prime minus 2xy prime equals 2y minus x squared. Now notice in these I didn't try to combine them or anything, I just put it together. Now this is the step that's a little bit tricky, and if you took college algebra and remember the inverse functions, we used a similar trick. You get the variable you want and factor it out. We're trying to solve for y prime. We get y squared minus 2x. Divide both sides by y squared minus 2x, and we have the derivative. Y prime equals 2y minus x squared over y squared minus 2x. That's a little bit complicated, but unfortunately these problems just take time. After you've done enough of them, you'll find that they can be done. Next question is find the equation of the tangent line. Same thing, we'll plug in 3, 3 into this. I get 6 minus 9 over 9 minus 6. That's negative 3 over 3, which is negative 1. That's the slope. Now, the line is going through 3, 3, so y minus 3 is going to equal negative 1 times x minus 3. Y minus 3 equals negative x plus 3. Y equals negative x plus 6. That's the tangent line. This was the derivative for this function. Next example. We've got 1 plus x equals sine of xy squared. Let's take the derivative with respect to x. The derivative of 1 is 0, and the derivative of x is 1. Now we've got this function here, and I've got really like a sine of u. We've got a function within a function. So the derivative of sine of u is cosine of u times the derivative of the inside. There's your chain rule. Let's take care of this derivative. This is a product. Remember, x times anything with y is a product. Y is a function of x, so let's use the product rule. Derivative of the first times the second plus the derivative of the second times the first. Just rewriting some of this. The derivative of x is just 1, so I'm left with y squared. The derivative of y squared is again that chain rule idea, but it's just a general rule, 2y times y prime, x. Let's multiply this out to get this to work. 1 equals y squared cosine of xy squared plus 2xy cosine of xy squared y prime. Now go quickly back and just check to make sure that I did that so that it makes sense to you. I distributed the cosine xy squared through and just rearranged a couple of numbers to make this easier. Let's solve for y prime. I'll subtract this term from both sides and I get 1 minus y squared cosine xy squared equals 2xy cosine xy squared y prime. Now divide everything by the 2xy cosine xy squared. And then finally I can write my answer. Y prime equals 1 minus y squared cosine of xy squared over 2xy cosine of xy squared. One more example. This one has a lot of products in it, so it might have a lot of terms, but it shouldn't be a very hard process. The derivative of 2x cubed is 6x squared. Hopefully you guys are getting really fast at that now. Plus, we have a product rule. The derivative of the first times the second plus the derivative of the second times the first. All right, minus, we have another product. Derivative of the first times the second plus the derivative of the second times the first. And the derivative of 2 is 0. Now, I was very deliberate with these brackets because this product rule is creating a derivative that's a single part of what was originally here. For this one, it didn't matter with the brackets, but for this one, you have to subtract the entire derivative. That's why I put this term in brackets. Anyway, let's keep cleaning up. 6x squared. Now this one I can just drop the brackets because it doesn't make a difference. I get 2xy plus y prime times x squared. Then this one I'm going to distribute the negative sign. I get minus, the derivative of x is just 1, so minus y cubed minus, from the distributing the negative sign, I get 3y squared y prime times x. There's a lot of terms, but it's not as hard as it looks. Let's just rewrite this to make it as clean as we can. I'll even rearrange it a little bit. 6x squared plus 2xy minus y cubed minus, I'm doing this term now, 3xy squared y prime, and then we've got a plus x squared y prime. Just take a moment to make sure that I did that correctly, that I just rearranged terms in a few variables. And now what I'm going to do is add this to both sides, the 3xy squared y prime, and subtract the x squared y prime from both sides, and we're left with the following. We have 6x squared plus 2xy minus y cubed equals 3x y squared y prime minus x squared y prime. And now we'll do the same thing as we usually do. Factor out the y prime. I get y prime times 3xy squared minus x squared. Divide and we get y prime equals 6x squared plus 2xy minus y cubed over 3xy squared minus x squared. That one just had a couple of product rules in it. Just be careful when you do these. This is something that we can use now that we have the idea of implicit differentiation, but it's not hard implicit differentiation. Here's the trick. Anytime you have a function raised to a function power, you can use logs because powers can come in front. What I'm going to do is take the natural log of both sides. And then using the properties of logarithms, I can write this as x natural log of x. That's helpful. Now I can take the derivative, but again I'm using implicit differentiation. This is probably a little bit rusty to you. Just remember, for implicit differentiation, we remember that y is a function of x. The derivative of natural log of y would be 1 over y, but then y is a function of x, so by the chain rule we get a y prime. And the rule that you were accustomed to is take the derivative of the function and then multiply by y prime anytime the function's in terms of y. On the right side, we'll use the product rule. We get the derivative of the first times the second plus the derivative of the second times the first. And now let's just clean all this up. 1 over y, derivative of x is 1, natural log of x. And the derivative of natural log of x is again 1 over x times x. So we get y prime is equal to natural log of x plus 1. And what I'm doing right here is I'm going to multiply both sides by y to get y prime by itself. Here's what we get. I get y, but y was x to the x. That's logarithmic differentiation. You take the natural log of both sides and then take the derivative implicitly, and once you get y prime by itself, you can actually plug the original y back in. This is the derivative of x to the x. You wouldn't really expect it to look that way, but it turns out to be the case. Next example. Logarithmic differentiation is also useful when you've got too many products and quotients floating around and powers. Let me call this thing y, which will help me. Then the natural log of y would equal the natural log of all this. So let's just write it out. Natural log of x cubed plus natural log of square root of x squared minus 3. We're separating with our log rules. Minus natural log of x minus 7 to the third power. When I took the log of both sides, I split the numerator into two pieces with a plus, and the denominator becomes a minus. Let's deal with these powers. So natural log of y equals 3 natural log of x plus 1/2 natural log of x squared minus 3. And then the last one is going to be minus 3 natural log of x minus 7. Now I can take the derivative. So 1 over y, y prime, just like last time. 3 times the derivative of natural log of x is 1 over x plus 1/2. The derivative of natural log of u is 1 over u times the derivative of u minus 3. Then the derivative of natural log of u is again 1 over u times the derivative of u. So we get 1 over y, y prime equals 3 over x plus 1 over 2x squared minus 6. The derivative of x squared minus 3 is 2x minus 3 over x minus 7. And the derivative of x minus 7 is just 1. So now we will multiply both sides by y to get y prime by itself. We get y prime equals 3 over x plus 2x over 2x squared minus 6 minus 3 over x minus 7, and it's all multiplied by y. Remember, y was x cubed times the square root of x squared minus 3 over x minus 7 cubed. And that's our answer. You could clean this up a little bit, it's not really worth doing.